Derivatives of determinants. I have divided this topic into two sessions, so let's get started. Before we jump into discussing the derivatives of determinants, I would like to quickly recap the various possible cases of finding the derivatives of vectors. I'm assuming here the elements of vectors x are independent of each other. Quick note, vectors will be denoted with bold small letters and scalars will be represented as small letters. The matrix will be represented in capital letters. Coming back to our discussion, the most basic assumption for vector differentiation can be represented as case first, del of bold letter x upon del y in square brackets subscript I equals del x subscript I upon del y. Case second, del of x upon del of bold letter y in square brackets subscript I, which equals del x upon bold del of y subscript I. Case third, del of bold letter x upon del of bold letter y in square bracket subscript I j, which equals del of bold letter x in square bracket subscript I upon del of bold letter y in square bracket subscript j. We will be discussing all the three cases in details in the next few slides. Let us consider two vectors x and y. Vector x is given by x1, x2 until xn. Vector y is given by vector y1, y2 until some ym value is obtained. Let us suppose each component of yi is the function of xj. This means y is a function of x, and mathematically we can represent this as y equals y of x. If n equals 1, x reduces to a scalar which we call as x, and if m equals 1, y reduces to a scalar which we call as y. Coming back to our discussion from the first slide, we have seen we have three cases to consider for vector differentiation. First one being derivative of a vector with respect to a vector, derivative of a scalar with respect to a vector, and derivative of a vector with respect to a scale. Let us start by understanding the first case, that is finding the derivative of a vector with respect to another vector. Here we have del bold letter y upon del bold letter x, and we need to find the derivative of vector y with respect to vector x. Please recall from our previous discussions that we have a vector y which equals y1, y2 until some value ym, and x equals x1, x2 until some value of xn. Here we need to find the partial derivative of vector y with respect to vector x. So let us understand in steps what is going to be the partial derivative of vector y with respect to x. Step first, calculate the number of rows in the final output. For this step, we need to see the denominator vector. So here in del y upon del x, the vector in denominator is x, correct? So x has n number of values. We've already seen that. That's as per our definition, correct? So the number of rows in our final output will actually be n. Now step 2. Calculate the number of columns in the final output. For this step, we need to find the numerator vector. In del y upon del x, the value in numerator vector is y. So y has m number of values. So the number of columns in the final output will be m columns. Okay, so this will be m columns. So the final output on finding the partial derivative of a vector with respect to another vector will be an n cross m matrix, which basically means that n is the number of rows, which equals the denominator vector x in this case, and y equals the number of columns, which is in the numerator. So the final output can be represented as del y1 upon del x1, del y2 upon del x1, so on and so forth until del ym upon del x1. Moving to the next row, we have del y1 upon del x2, del y2 upon del x2, going forward until the column ym is obtained, so del ym upon del x2. Similarly, this will be iterated until xn rows. Remember, we have xn rows. This is a vector which has n number of rows. So the final value in the final row shall be del y1 upon del xn, del y2 upon del xn, and this will iterate until del ym upon del xn is obtained. Let us move to the second case. In this case, we will be finding the partial derivative of a scalar with respect to a vector. So here we have del y upon del bold letter x. Please note, bold letter denotes a vector. So in this case, in numerator, we have a scalar value which will always be 1. It will always be one single value. And in vector x, we have n number of values. This is as per our previous definition. That is x equals x1, x2 until some value of xn. So now let us use the same set of steps we used while finding the partial derivative of one vector with another. Though in this case we have a scalar value in the numerator. That's the difference. So step first, look for the value in the numerator. In this case we have a scalar value which means that at any point in time we'll only have one single value, correct? So this means we'll only have one column in our final output. Step 2, look for the value in denominator. In denominator we have a vector x which has n number of values, correct? So this means the number of rows in the final output will be n. So the final output will be a matrix or a vector which will have n cross 1 dimension. This can be represented as del y upon del bold letter x equals del y upon del x1, del y upon del x2 until del y upon del xn is obtained. Let's address the final case where we are finding the partial derivative of a vector with respect to a scalar value. This will be represented as del bold letter y upon del x. Let us now use the same set of steps we followed in the other two cases to find the dimension of the output matrix. So step first is we have a vector y in the numerator which has m number of values as per our previous definition, y1, y2 until ym. So basically this means that we will have m number of columns in the final output. Step second, we have a scalar value x in the denominator. So the scalar value at any point in time will just be one single value. So we'll only have one single row in the final output. So the final matrix or vector should look something like this. Del bold letter y upon del x equals del y1 upon del x, del y2 upon del x until del ym upon del x is obtained. Let us take an example to understand this in a bit more detail. So here we have two vectors x and y. Y has two variables y1 and y2 and x has three variables x1, x2 and x3. We are also given that y1 equals square of x1 minus x2 and y2 equals square of x3 plus 3 times of x2. Now we need to find the partial derivative of del y by del x. That is, we are finding the partial derivative of vector y with respect to another vector which is del x. Now let's start with the steps that we've learned. Step first is we have a vector y in the numerator and vector y holds two values which is y1 and y2 respectively. That means we'll have two columns in a final output matrix. Step second, we have a vector x in the denominator. Vector x holds three values x1, x2 and x3, which means we will have three rows in our final output matrix. So the partial derivative of vector y with respect to vector x will be given by del Del y upon del x equals del y1 upon del x1, del y2 upon del x1, del y1 upon del x2, del y2 upon del x2, del y1 upon del x3, and del y2 upon del x3 respectively. Let us now differentiate del y2 upon del del y1 with respect to del x1. So the value of y1 here that we have is square of x1 minus x2. So when we find the partial derivative of y1 with respect to x1, we'll have 2 times of x1, and when we'll try to find the partial derivative of x2 with respect to x1, it will be a 0. So this gives us 2x1. Similarly, if we have to find the partial derivative of del y2 upon del x1, the definition of y2 equals square of x3 plus 3 times of x2. So in this entry, we do not have an x1 value, correct? Because this is x3 and this is x2. So finding the partial derivative with respect to x1 will be 0 in this case. So 0 plus 0 will be a 0 value here. Moving on to the next row, del y1 upon del x2. So again, finding the partial derivative with respect to x2. So the value in front of x2 is basically minus 1. So finding the partial derivative will give us a minus 1 here. Similarly, finding the partial derivative of del of y2 upon del of x2 will give us a 3 here because we have x2 as a coefficient, and finding the partial derivative of x3 with respect to x2 will give us a 0. So the final output shall be 3 in this case. Similarly, moving to the next row, del y1 upon del x3. y1 has no x3 entry, so we'll have a 0 right here. Similarly, for y2, we have x3 squared. So we'll find the partial derivative of this value, which will give us 2 times of x3. Let us now take a second example. In this example, let's move back to the scalar derivative rule. Let us take a linear function f of x, which has been defined by f of x equals a times x. The partial derivative is given by del f upon del x, which equals a. One important relation to remember. If we have to extend this function to a multivariate case, please note a multivariate is when we have multiple input values given to the function. So I can extend this function as f of x equals summation of a of x, ai xi equals transpose of a times x. So our expression, this f of x that we've written in the form of a multivariate function, can actually be simplified as a equals a1 a2 until some an transpose value, and x equals x1 x2 until some xn value is obtained, which is also transpose. So if we continue to expand on this example and are finding the partial derivative of del f with respect to del x subscript k, we'll get the constant a subscript ak. So now we are finding the partial derivative of the whole multivariate values that we've taken with respect to x of k. So we'll assume that, let's suppose we start with a1 x1 plus a2 x2, and this extends until some value ak xk plus some value, let's suppose that an xn is our last value. So when we are finding the partial derivative of all these expressions with respect to del of x subscript k, we'll only have a constant a of k. For rest of these entries, we'll have a 0 because x we are having the constant as x1, and finding a partial derivative of x1 with respect to xk will be 0. Similarly, x2 with respect to xk will be 0. So whatever this value of k is, only for that specific coefficient you will have an output outside, which is a of k in this case. Now let us further do one thing. Let us assume that k has entries from 1 to n, and then we organize the partial. Now we are finding the partial derivative of n entries in this case. So this can be represented as del f upon del x1, del f upon del x2 until del f upon del xn is obtained. And so the final output will be a1, a2 extended until an, which also equals a. So as you can see that even for multivariate situation and for single input function, the output in both the cases equals A. Some very important points to remember. For a scalar valued function f of x, the result del f upon del x has the same size with x. We've already seen this point multiple times in the past few examples. If there's a multivariate scalar function f of x equals transpose of a times x, we have del f upon del x equals a. We've also seen this just in the previous slide. This is because transpose of a times x is scalar, and we can write it equivalently as the trace of its own value. Okay, so keep this in mind. This is a very important point, that transpose of a times x, if you're finding the partial derivative of this function with respect to x, you get a in the output. It's because when you multiply the two, you get a scalar value. Okay, so if there's a multivariate scalar function, f of x equals trace of transpose of a times x, which also equals del f upon del x equals a. So one important thing that you should really keep in mind, and I should explicitly point out, is that transpose of a times x equals trace of transpose of a times x. This is because we've already seen that transpose of a times x gives us a scalar value, and that is why trace of transpose of a times x also equals this entry. Okay, so you have to keep in mind that transpose of a times x equals trace of transpose of a times x, and since both of them are equal, we've already seen when we find the partial derivative of this expression with respect to x, we actually get an a. And since this equals this, so if we try to find the partial derivative of trace of transpose of a times x, we'll still get a in the output. Okay, if there's a multivariate scalar function f of x which is given as trace transpose of matrix A times x, we have del f upon del x equals a. Here a and x can be matrices. So these two relations, this one, the third one and the fourth one, they're pretty much the same. The only difference here is that you have a matrix in this case. So if you're finding the partial derivative of a matrix transpose matrix times x, you'll have the matrix back. A is the output. And trace of a square matrix is defined as trace of A equals summation of I ai A double I. Basically, you are doing a summation of all the diagonal entries, and that's how you represent a trace of a square matrix. This notation is important when deriving matrices with eigenvalue. So that is why I'm explicitly mentioning this right now. Okay. So now let's take an example. We have A as a matrix, and you're finding the partial derivative of trace of matrix A with respect to A. So this will give us an identity function back, because we know that trace just operates on the diagonal entries, and so we'll just have some diagonal values left, and that is why we will have an identity matrix back, because in identity matrix you have only ones in your diagonals and rest all the entries are 0. So revision of some important trace properties again. We really need to remember them. They are very important. I've already discussed them in the previous session where we were discussing some important nomenclature, but since we'll be needing them again, I'm just doing a quick recap. So if A and B are matrices with proper sizes and C is some scalar value, so trace of A plus B equals trace of A plus trace of B. Second point, trace of scalar C times A, you can take the scalar outside, so C times trace of A. Similarly, trace square bracket AB equals trace of B times A, it's commutative. Trace of A1 into A2 means you're multiplying them until AN equals, this is always a property of trace, you can just bring in the last entry and then just keep multiplying the rest of the entries directly, which equals trace of AN. So the last entry is brought at the first, and then rest of the entries are just multiplied successively. Similarly, fifth point, trace of transpose of A times b equals summation of I summation of j a subscript ij times b subscript ij, and trace of a equals trace of transpose of a. This property 6 is an important property because you're just doing a 45-degree shift when you are actually finding the transpose, and since it's traced with just the diagonal entries, and since the diagonal entries are going to be the same, so this relation right here, 0.6, is an important relation that we should keep in mind. Okay, so let's take an example here. So for vectors a comma x, so we have two vectors here, a and x, and the function is defined as f of x equals transpose of a times x. We need to find the partial derivative of del f upon del transpose of x. Okay, so we can write this function as del transpose of a times x upon del transpose of x. When we are finding the partial derivative, we're going to be using all the properties here, okay, which we've already discussed a couple of times in the previous slides. I'll just keep switching back between the previous slide and this slide just to make sure which properties we are using. So now this value right here, transpose of a times x, can also be represented as trace of transpose of a times x, correct? We've seen this in this slide right here, this property where we said that transpose of a times x equals trace of transpose of a times x, because multiplying this entry gives us a scalar value. That is why the two values are equal, correct? So as per that property, can I actually replace transpose of a times x with trace of transpose of a times x? Yes, I can. And then we are finding the partial derivative of this whole expression with respect to transpose of x. Now we know that the transpose function is actually commutative, so I can reverse them, I can swap these entries, and so transpose of a times x can also be represented as x times transpose of a, and then we are still finding the partial derivative with respect to transpose of x. Now we also know that we've also seen in the property that x equals x of, so sorry, transpose of x equals, I'm sorry, trace of x equals trace of transpose of x. Sorry, there are too many similar terms with respect to pronunciation, so it just skips. So let's be specific again. Trace of x equals trace of transpose of x. These two entries are equal. We just saw this in the 6th point, remember. So now can I actually write this trace of, so independently, if I have to write, can I write trace of x equals trace of x t as per property 6? That's what I've done. I've just swapped them again, and then I have interchanged these values. So what I have is transpose, trace of transpose of a becomes trace of a, and trace of x becomes trace of transpose of x. Again, we are finding the partial derivative with respect to transpose of x. Now as per the, as per the transpose rule, a transpose t, if you have this entry, this can be represented just simply as a of transpose. But if you have a, then you can actually write this as a of transpose of transpose. So if you transpose the same vector twice, then it gives you the original vector back, right? So can I actually write this a as transpose of a times its transpose, and then transpose of x is intact, and then we are finding the partial derivative with respect to transpose of x. Now if let's just simplify the whole expression, let's do one thing here. Let's replace transpose of a with some capital A. Okay, let's just represent this here. So this final expression, the second last expression, can be simplified as del trace this is capital A transpose xt upon del of transpose of x. Now this expression should look really similar to one of the points we discussed, and the point is this one. So if there's a multivariate scalar function f of x which equals trace of transpose of a x, we have del f upon del x equals equals capital A, which is the matrix. So if we pay close attention to this representation or the final value that we have obtained, it is transpose of A times transpose of x. This whole operation is squared under the trace operator. So can I actually remove trace of x of transpose as trace of x? Yes, I can do that, correct? Because as per property 6, both of these values are equal. So I can actually replace this transpose, and now I'm finding the partial derivative of trace of transpose of A times x with respect to transpose of x. So now I know that this value is A in the output, correct? Because this is our original derivation that we derived, right? Transpose of A times x gives you the value A back. So I've gotten an A in this case, right? Now we know that the value we substituted in place of a capital A is transpose of A, and that is what I have gotten as the output. So you see that whatever tips and tricks we've actually listed in the previous slides is very handy and useful in solving different kinds of questions. And few of the most important properties that we've actually used is this property 6 right here, that is the trace of your matrix A equals trace of transpose of matrix, and some of the properties which we discussed right here. This one, that is the transpose of A times x equals the value A in itself, and that trace of A times x equals transpose of A times x equals trace of transpose of A times x. And then this final value right here, where we say that f of x equals trace of transpose of A times x. Okay, so these properties are important that we should keep in mind, because we will be using them interchangeably while solving the questions, different kinds of questions. So this is pretty much it for this session. In the next session, we will be doing a quick revision of what is the difference between differential and derivative. We will also be covering different ways where we represent differential and how we represent a derivative. We will then see the relationship of matrix differentials. There will be some important points that we have to keep in mind, and some important relationships between the differential operator and the partial derivative operators. And then we will also be solving problem statement 0 from CS 229 Stanford class by Andrew. This is from a fall 2018 class, but I think 2019, 2020 pretty much they have the same syllabus. So we will be discussing those questions as well in the next session. So this is pretty much it for this session. I hope we will stick around for the next session as well, because we're covering all the important aspects we need to keep in mind while finding the derivative of a determinant. And I've tried to summarize all important formulas and relations and all kinds of examples, so that when we are applying them to different kinds of problems, we have a handy tutorial in place, and we just know what we're doing. So yeah, thank you so much, and I look forward to continuing the part 2 of this video session.